The next era of the Archean is the Paleoarchean, which spanned from 3.6 to 3.2 billion years ago. The hafnium isotope record indicates that continental crust was beginning to form at this time. This was the result of increased crust-mantle differentiation, as lighter elements, those which constitute felsic rocks common in continental crust, became relatively more abundant on the surface, and the mantle became slightly denser. On the modern Earth, there are core regions of continents known as cratons, composed of very ancient rocks, and the Pilbara Craton in northwest Australia and the Katval Craton in southern Africa formed during this time period. These two cratons may have formed the proto-supercontinent of Volbara. This would have been a supercontinent in the sense that it included the majority of land on Earth at the time, but it still would have been smaller than any continent on Earth today. As the crust became less dense, it also became less mafic, and serpentinizing systems wouldn't have been as abundant as they were in the Eoarchean. But the overall rates of serpentinization would still be over half what they were previously. Volcanic activity was driven primarily by hotspots, which were far more abundant than they are today. It's from Paleoarchean age deposits that we find the oldest sedimentary rocks, but very few rocks remain from the first 100 million years of the era. The Paleoarchean saw the emergence of dissimilatory sulfur metabolism, and this is inferred by sulfur isotope systematics. Before we get into that, it's important to go over how isotopes work. The relative abundance of an isotope is given by the delta notation, and the units are per mil. To get this, we first have to get R, or the abundance of the isotope in question divided by the abundance of the most abundant isotope. The delta value of that isotope is equal to the product of 1 subtracted by the ratio of the sample divided by the ratio of a standard and 1000. The standard for sulfur isotopes is the Cannon-Diablo triolite, a fragment of the meteorite which created Meteor Crater in Arizona. Sulfur has 4 stable isotopes: sulfur-32, which has the greatest abundance at 95.02%, followed by sulfur-34 at 4.21%. The third most abundant isotope is sulfur-33, and the least abundant is sulfur-36. Chemical processes which reduce sulfur to sulfides will select for the lighter isotopes, and this is exacerbated by biological sulfur reduction. Conversely, oxidizing sulfur will select for the heavier isotopes, but biotic oxidation won't change the isotopic composition. Most processes which fractionate sulfur isotopes follow a pattern known as mass-dependent fractionation. This is where the change in the abundance of the various isotopes is directly proportional to their mass. If a sample of sulfur is subjected to a mass-dependent fractionation process, the resulting delta-34s and delta-33s values will fall on the MDF line, and if the delta-34s value is on the x-axis and the delta-33s value on the y-axis, the slope of this line is 0.52. What determines the slope is the difference in mass of sulfur-33 and sulfur-32, the most abundant isotope, divided by the difference in mass of sulfur-34 and 32. Mass-independent fractionation will produce a material with a relative isotopic abundance that does not fall on this line, and how far it deviates is denoted by a capital delta, in this case, cap delta 33s. Very few processes result in mass-independent fractionation, but one of these is the UV photolysis of sulfur dioxide. Here, UV photons strike atmospheric sulfur dioxide molecules, producing elemental sulfur and sulfate. The elemental sulfur is anomalously enriched in sulfur-33, while the sulfate is depleted. Mass-independent fractionation can also be measured via sulfur-36, but in a different manner, and when these are plotted, the sample subjected to photolysis will fall on another slope or array. The slope of this array will vary between different UV wavelengths. Polar coordinates can be used to identify which array a sample is on, or instead of using the distance from the x and y axes to describe the position, The angle relative to the x-axis and the distance from the center can be used. Samples subjected to mass-independent fractionation will also fall on specific arrays when using delta 34s and plotting it against cap delta 33s. How did dissimilatory sulfur metabolism itself begin? An enzyme, which is found in virtually all sulfur metabolizing organisms, is dissimilatory sulfite reductase, or DSR. This enzyme will take 6 electrons to reduce a sulfite to a hydrogen sulfide. In volcanic vents, sulfur dioxide from the magma will react with water to form sulfite, which is highly toxic to pretty much every organism. Methanogens, which inhabit these systems, often possess DSR-like proteins, which are essentially simplified versions of DSR. These possess a single subunit and float around within the cytoplasm. They perform the same reaction as DSR and obtain electrons from an unknown cytoplasmic electron carrier, while some possess iron-sulfur clusters to facilitate the flow of electrons within the enzyme. One lineage of these, known as DSR-like 2 proteins, underwent a gene duplication to form the A and B subunits of DSR. This was bound to the HDR of methanogenesis, where the disulfide bond between coenzymes B and M are reduced and split by electrons from the electron transport chain. The DSR-C subunit, which takes electrons from the electron transport chain in sulfur-aspiring organisms, is homologous to HDR. This would have coupled the ancestral DSR to the central energy metabolism, allowing sulfite to act as the terminal electron acceptor. So, like autotrophic methanogens, the first dissimilatory sulfur metabolizing organism likely used molecular hydrogen as the electron donor. The addition of non-carbon electron acceptors paved the way for the earliest form of respiration. Because sulfur is more electronegative than carbon, using sulfite as an electron acceptor from organic carbon will produce energy. Of course, this would require enzymes that can take electrons from carbon to be fed into respiratory pathways. Many biosynthetic pathways involve reactions that couple partial oxidation and reduction of carbon groups on molecules, and one of these enzymes, which took electrons off a carbon, could then pass them off to an electron carrier, which would ultimately take it to sulfite in the DSR complex, giving rise to the first form of respiration. While aerobic organisms nominally completely oxidize carbon via the TCA cycle, anaerobic respirers, those that use an electron acceptor besides oxygen, usually only partially oxidize carbon. These organisms don't have a set carbon oxidation pathway, and instead have an assortment of enzymes which take electrons off various organic molecules, and this can be seen as an intermediate between early biological redox coupling as part of biosynthesis pathways and an entire system to completely oxidize carbon for energy. Apart from having the DSR-like proteins, which acted as the progenitor to the first respiratory enzyme, several key features of respiring organisms originated in methanogens. One of these are electron carriers which reside within the cell membrane, the aforementioned MPH2. Methanogens also sometimes possess seroheme-containing membrane-bound cytochromes to facilitate electron transport and ion pumping, and another membrane-bound electron carrier known as menaquinone, which is common in anaerobic respirers. However, it's hard to say whether these arose in methanogens and were inherited by respirers, or if they began in respirers and were transferred horizontally to methanogens. Although the advent of respiration would allow early life to utilize more energy, using sulfite as an electron acceptor would be inherently limited due to its toxicity. However, geochemical processes can produce other oxidized sulfur species. For one, calcium oxides will react with sulfite to produce sulfate ions, and in alkaline environments, sulfide ions will react with sulfite to form thiosulfate. Thiosulfate reductase reduces thiosulfate to sulfide and sulfite, and this is in the molybdopterin oxidoreductase enzyme family. Thiosulfate reduction likely began when an arsenite oxidase enzyme was bound to the respiratory electron transport chain and began to metabolize thiosulfate due to its similarity to arsenate, although this would have reversed the direction of the reaction because the enzyme complex would be taking electrons from the electron transport chain and imparting them onto the metabolite instead of taking them from the metabolite, which would have been previously arsenite. Two other sulfur metabolizing enzymes closely related to thiosulfate reductase are tetrathionate reductase and polysulfide reductase. Using sulfate as an electron acceptor would have involved two steps. First, a kinase enzyme phosphorylated sulfate with an ATP, giving rise to sulfate adenyltransferase. Second, a flavoprotein reduced it to sulfite, which ultimately evolved into adenyl sulfate reductase. The fact that the reduction of sulfate and thiosulfate includes a sulfite intermediate, which is then reduced to sulfide by DSR, further indicates that sulfite reduction was the earliest form of dissimilatory sulfur metabolism.